What we're doing in the next few sections is we are introducing other ways that we can use matrices to also solve systems of equations. So we're kind of learning some new tools with matrices that will allow us to do the thing we've already done. So if you think back to section 8.1 when we worked with row echelon form and reduced row echelon form, we can take a system of equations, 2 variables, 3 variables, and higher. We can write it as an augmented matrix, and we can perform the row operations to get it into REF or RREF, and then we can solve by back substitution. So the next method that we're going to start talking about today is solve matrix equations, which represent our systems of equations, and what we need in order to be able to do that is something called an inverse matrix. So up at the very top, we've got a box here, and we're going to fill in some blanks, so follow along with me and fill them in. The first one will start a square matrix. Sorry. And notice it's n by n, so that would imply its rows are equal to its column. That consists of ones along its main diagonals and zeros everywhere else is called an identity matrix. Okay. So if you have a diagonal of 1 in a square matrix, zeros everywhere else, we'll call that the identity matrix. So there's an identity matrix for 2 by 2, 3 by 3, 4 by 4, 5 by 5, and they all look the same. Diagonal ones, zeros. Okay. So here's an example of an identity matrix for a 3 by 3 square matrix. And notice it's being labeled I. So this is a capital I. Anytime you see capital I, then we're talking about the identity matrix. Now note it says off to the side, a matrix A, because capital A is matrix A, times the identity, is the same as the identity times matrix A, which is basically equal to A. So if I were going to pick, like this is a 3 by 3 matrix, so I'll put in that same matrix. And maybe I want to multiply it by a 3 by 2. I'll put 1, 2, 3, 4. No, I put in too many 2's, didn't I? 1, 2, 3, 4, 5, 6 is what I'll put in. 1, 2, 3, 4, 5, 6. Okay. So think about, like, can you multiply these two matrices? This is 3 by 3 times a 3 by 2. Yes, I should be able to multiply them. And my answer will be a 3 by 2, the outside dimensions, right? And if I did multiply, so I would start by taking this first row, 1, 0, 0, and I would multiply it by this first column. Well, that would be 1 times 1 plus 3 times 0 plus 5 times 0. So doesn't that just equal 1? And then I'll take that same row, 1, 0, 0, and multiply it by the second column. That'll be 1 times 2 plus 0 times 4 plus 0 times 6, which is just 2. And now I'll go grab the second row, 0, 1, 0. Multiply it by this column. 0 times 1 plus 1 times 3 plus 0 times 5. That's just 3. Take that second row times the second column. 0 times 2 plus 1 times 4 plus 0 times 6. That's just 4. Do you see how we are basically getting back the same entries that is matrix A? So we would expect the last row to be 5 and 6. And so take, oops, sorry, is that why you guys were all staring at me funny? There should be a 0 there. Saw something strange in your eyes and thought, this is not hard. Okay, I get it. Okay, the last row would be 0, 0, 1. I apologize for that. But we would take that and we would multiply it by all the entries in the column. So 0 times 1 plus 0 times 3 plus 1 times 5. That's 5. 0 times 2 plus 0 times 4 plus 1 times 6. That's 6. So it's saying if you take a matrix A, this 3 by 2, 1, 2, 3, 4, 5, 6, and you multiply it by an identity matrix, you will get the same thing. It's just like if you think about with real numbers, there is an identity property for multiplication with real numbers. Any number times 1 is just itself. 5 times 1 is 5. 8 times 1 is 8. Okay, so that's the identity matrix. The identity matrix has some correlation to our inverse matrix. So the next box is all about inverses. Let A be n by n. So what are we saying about A? A must be a square matrix. And let I sub n be the n by n identity matrix. Remember, anytime you see a capital I, you would assume that's an identity matrix. The I sub n is just saying, like, if A is 2 by 2, then you're going to use the 2 by 2 identity. If A is 3 by 3, then use the 3 by 3 identity, so on and so on. Okay. If there exists an inverse matrix, and we'll use the notation A inverse. So it looks like it has that negative 1 exponent. We saw that with function notation. We would call it like f of x, f inverse x, if we put the little negative 1 there. Okay. So we just call that A inverse. Then the following must be true. A matrix A times its inverse is the identity matrix. And you can even multiply it the other way. So we said last week, like, matrix multiplication is not commutative unless it's a matrix and an inverse matrix. The inverse matrix times A is also the identity matrix. So it doesn't matter which order you multiply them, you will get the identity matrix. And, that is true about real number inverses as well. There's a multiplicative inverse for every real number. Like, the multiplicative inverse for 2 is 1/2. Because 2 times 1/2 gives me 1, the identity value. Okay? So inverses are things that undo each other. A non-square matrix cannot have an inverse. So if it's not square, I'm not going to ask you about an inverse. And strange, not all square matrices have an inverse. So only square matrices have inverses. But at the same time, not all square matrices have an inverse. So sometimes you'll have an inverse, sometimes you won't for a square matrix. Okay. Now the next box is about how to find the inverse for a 2 by 2 matrix. So you might want to make a little note in here that this is going to be no calculator. 2 by 2s, I can ask you to do by hand without a calculator. And you use this little formula or setup. Okay. Now, essentially, where does this come from? It's from the solving of the systems. So if you want to see the proof for the 2 by 2 square matrix, we can look at that. I think we'll have time on Wednesday. I want to respect your time today, so we probably won't get to it today. Okay, do you see I have matrix A with entries A, B, C, D? If you want to find its inverse matrix, so A inverse, you have to first find this scalar out in front, which is 1 over AD minus BC. So look back at matrix A and see where you'll get AD and BC. You are multiplying the values on the two diagonals, right? So A times D, the diagonal going down from left to right, minus, and then you do B times C, the diagonal going up from left to right. Okay. So if you want to, you can make a little note right there. This is the difference of the product of the diagonals. The other thing really important, and this is like where homework comes in handy because you'll practice it so you'll know the setup, you have to change the entries as well as multiply by the scalar to write the inverse matrix. So notice on that first diagonal, A and D switch positions. Okay, so the value in the bottom right moves to the top left and vice versa. So they're going to swap spots. What happens on the other diagonal to B and C? They change signs. Now they might already be negative, so then you make them positive, right? So you change the signs on the other diagonal. But don't move B and C, they stay where they are. They only change signs. So we'll go through real quickly the two inverses down here. So this is like our matrix A. We want to do A inverse. So that's 1 over 6 minus 2. The difference of the product of my diagonals. Times, on this first diagonal, switch the positions of 2 and 3. And change the signs on the other diagonal. So they were both negative, now they're both positives. Well, this is really 1 over 4, right? So now I've got to distribute my scalar to each of those. That will be 1/2, 1/4, 1/2, 3/4. And there's my inverse matrix. Okay, any questions? Just real quickly, I'm going to take my original matrix, which is 3, -1, -2, 2. I'm going to take my inverse matrix, 1/2, 1/4, 1/2, 3/4. And I already kind of know what should happen, but I just want to illustrate one more time, like what are the properties of these inverse matrices. If I multiply a 2 by 2 by a 2 by 2, I'll get another 2 by 2. Okay, for my first entry, take my first row, 3, -1, and multiply it by 1/2 and positive 1/2. Okay. So that would be 3/2 minus 1/2, which is 2/2 or 1. And then I take that first row, 3, -1, and I multiply by 1/4 and 3/4. So 3 times 1/4 is 3/4. -1 times 3/4 is -3/4, which is 0. And then I would take the second row, -2, 2, and multiply by the first column. -2 times 1/2 plus 2 times 1/2, 0. -2 times 1/4, that's -1/2. Plus 2 times 3/4, that's like 6/4 or 3/2. So that's -1/2 plus 3/2 or 2/2, which is 1. So when I take a matrix times its inverse, I get the identity matrix, right? So that's its like property. Okay. You don't have to check that every time you do an inverse. I just wanted to like point out like that's true, right? It's working. Okay. Some of you may have worked ahead. If you haven't, maybe take a quick minute here. See if you could get going on the inverse. Something interesting happens. This is my A, so I want to do A inverse. It'll be 1 over 6 minus 6. What's interesting about that scalar? 6 minus 6 is 0. So you have something 1 divided by 0, which is not 0. It is undefined. Does it really matter what I put in here if I'm multiplying by something undefined? There is no inverse. So remember I said only square matrices will have inverses. And we could do 2 by 2s by hand. But not all square matrices actually do have an inverse. So this is an example when you don't have an inverse. You could kind of write a rule for yourself. Anytime AD minus BC equals 0, no inverse, because then your scalar is undefined. Okay, any questions about that 2 by 2 business? Okay, on the back side, we're going to do some calculators, and then we're going to do a no calculator solving example and a calculator solving example. So go ahead and pull out your calculators. Basically, the new part of like how do you do the inverse matrix, it starts at like step 5. Like everything else is telling you how to get back to that matrix menu, which we did last week. But basically, you input your matrix, and we're going to do that one right below, which is a 3 by 3. And then you go back after you input the matrix, you call up matrix A, and then you use that inverse button that looks like x to negative 1. You just hit that button, and then it will do the inverse for you. So if everybody can edit matrix A and put in these values, 1, 2, 2, 3, 7, 9, negative 1, negative 4, 7. So second, x to negative 1, edit. We're going to do a 3 by 3. 1, 2, 2, 3, 7, 9, negative 1, negative 4. And then you'll exit out of the matrix menu, and you'll go back and you'll call up A, and then just use the same button you've been using to get to the matrix menu. Oh, you can go charge it over there. Maybe grab one from the bin. You should be practicing any calculator, Randall. If you need to borrow one, you come up and get one. Use your muscle memories. You should be typing this in. I will not tell you how to use the calculator during the test. I have given you ample time to figure it out. Okay, so I'm going to go to the matrix menu. I'm going to call up A. And then instead of doing second x to negative 1, I just hit that negative 1. It'll look just like my notation that I've been writing. There's my inverse matrix. Okay, let me know if you're not getting that value when you type it in. Want to help you? You got one? You do. Oh, did you put it in already? Oh, you gotta do second, x to negative 1. And then you gotta go over to edit. And then you're gonna make it 3 by 3. Okay? Okay. So if you wanted to check, is that really my matrix? Remember, the matrix or the inverse matrix times the original matrix. So if I go back, and I pull up matrix A, this would be like taking the inverse, because that's my previous answer, times A. It's the identity matrix, right? That's what inverses do. They multiply together and they make the identity matrix. So this one with negative 13, 6, 4, 12, negative 5, negative 3, negative 5, 2, 1. That's my identity matrix. I'm going to put that in right here just so we have it in our notes. Okay. So 3x3s have to be done with your calculators. To be real honest with you, I've never even done a 3x3 by hand. So, if Miss Cronky has made this far without doing a 3x3 by hand, you can too. Right? Okay. Madison's thinking she's going to set that as a goal. Okay, cool, that will work. All right, now we're going to do two solving equations or solving systems. And the first one would be no calculator. So if you'll set your calculators aside momentarily, okay, we'll do the 2x2 no calculator, and then we'll do the 3x3 with calculator. Okay, so remember, we're trying to do it a different way. We've already learned one way, which was row echelon form. We write an augmented matrix, we use row operations, we get it in row echelon form. Today what we are going to do is we're going to first write out a matrix equation. And our matrix equation is going to be A times X equals B. And notice A, X, and B, they're all capital letters, so they represent matrices, like they have some order and some inputs or entries. So A is your coefficient matrix. X is your variable matrix. And B is your constant matrix. So it's going to be a different setup than the augmented matrix. We're going to create three different matrices. So I'm going to take this system, 2x2, and I'm going to create my matrix equation. My coefficient matrix, my coefficients are in front of x's and y's. So that would be 1, 2, 2, 1. X's in one column, y's in the other. My variable matrix are my unknowns. This is two variables, so I just have x and y. If it were a three variable system, I would have a 3x1 matrix, x, y, z. And it equals my constant matrix, which is 7, 8. I can stop just for one moment and think about, like, why does writing out the matrix equation like that work? Think about matrix multiplication from Friday. I would take this row, 1 and 2, multiply it by this column, x and y. So 1x plus 2y would equal the entry over here, 7. That's the first equation. And then the second row times the column, so 2x plus 1y would equal the second row over here, 8. That's the second equation. Now, I'm going to go back over here to my matrix equation and think just back to like Algebra 1 and before. If you had a variable that was being multiplied by something and you wanted to solve for the variables, how would you get the variables all by themselves? Don't overthink it. If it was being multiplied by something, and you wanted to get it all alone, you would divide, right? Or like, what if your variable had something being added to it? What would you do? X plus 3 equals 5. How would you solve for x? You would subtract it, right? If something was being squared, your variable was being squared and you wanted to solve for just x and it was x squared, what would you do to both sides? Square root it. What you're doing in all of those scenarios is performing the inverse operation, right? The inverse of multiplication is division, the inverse of addition is subtraction, the inverse of squaring something is square rooting it. So over here in your matrix equation, to solve, you would want to multiply both sides by your inverse. So you want to perform the inverse operation, which in matrices is to multiply by the inverse matrix. Because on this left side, when I take A inverse times A, I'm going to get What always happens when I multiply an inverse by a regular matrix? I get the identity matrix. So it's the identity matrix times my variable matrix. And the identity times x is really just x. That's what I showed you on that very first one. So every time you want to solve a matrix equation, essentially you're doing all these steps. So you start here, matrix A times matrix X equals B. You multiply by the inverse on both sides. You get the identity, but then that's just the variable matrix. You don't have to do all that work. You just know. It's the inverse times the constant. So to solve, take the inverse matrix times the constant matrix. If we're doing this no calculator, then we need the inverse of A. So that's not too terrible. Here's A, right? A inverse would be 1 over 1 minus 4, which is negative 3. Got to distribute that, switch 1 and 1, but they're the same. Change the signs of the 2's. So I think my inverse will be negative 1/3, positive 2/3, positive 2/3, negative 1/3. What we did on the last page. Find the scalar, distribute it. And then I just need to say my variable matrix is equal to my inverse. Times my constants. Now you will always have to put your inverse in front of your constant matrix because your constant matrix is a column matrix, so it has a number of rows but one column. So your inverse always has to be in front so that you can actually multiply like the columns in your inverse match your rows in your constant. Before I do my multiplication there, have I lost anybody in what I'm doing? If so, you should ask a question. We might all benefit. I'm just taking the inverse times the constant. So now I just got to work it out. You might stop and think about this was a 2 by 2, this was a 2 by 1. So my answer is going to be a 2 by 1 in the end. Which makes sense. So I should have an x and a y. I should have only one entry in each row. So that's going to be negative 1/3 times 7 plus 2/3 times 8 for my first entry. And then it's going to be a 2/3 times 7 plus negative 1/3 times 8 for my second entry. Just doing matrix multiplication, which we practiced on Friday. And it can feel like, oh my gosh, what am I going to do with all these fractions? But if you keep the same denominator, it will actually work out really nicely. So like negative 1/3 times 7 is negative 7/3 plus 2/3 times 8, that's just 16/3. So then I have 9/3, or that's really just 3. And then when I do 2/3 times 7, that's going to be 14/3. Negative 1/3 times 8 is negative 8/3. So 14 minus 8, that's 6/3 or 2. So my solution is 3/2. Okay. Now on Friday's quiz, I think I do probably ask you like, solve this system using an inverse matrix or matrix equation. So then you have to do it this way so I know you're aware of what's going on. Okay? But I am also pretty sure on the test, which is next week, on the test, it will say something, it will give you a system like a 2 by 2 system, and it might say solve this system by using row echelon form or a matrix equation. So then you can choose whichever one you want to use. Okay, but you do want to practice all the methods that we do, because on the quiz on Friday you'll need to know all of them. Okay, does anybody have any questions about what happened right there? Okay, last example is 3-variable system. Okay. Well, if it's 3 variables, then your coefficient matrix is going to be 3 by 3. So my matrix equation would look something like this: 2, 3, 1, 3, 3, 1, 2, 4, 1. My variable matrix would be x, y, z. And help me out, is my constant -1, 1, -2? Get those right? Okay. The solution for a matrix equation will always be the inverse of matrix A times my constant. But I don't know how to do the inverse of a 3 by 3 matrix. So this is a calculator problem. So I can go to my calculator, and what I'll do is I'll input matrix A as is, 3 by 3. I will input matrix B in a separate location, and then I will call on the calculator to do A inverse times B by using the names menu. Okay, so I'll show you that really fast. I'm going to move this down so that I can see it when my, I can't move it all the way down. I'll pull up my calculator. I can still get it done. So second matrix, I'm going to edit A. And I'm going to put in those coefficients to the 3 by 3. So 2, 3, 1, 3, 3, 1, 2, 4, 1. Then I'm going to check on my matrix B. So here's one time where I have more than one matrix. Oops. I went and called on matrix B instead of editing, edit matrix B. So I've already got A edited. Now I check my matrix B. I just put in the constants there, -1, 1, -2. So it's a 3 by 1, 3 rows, 1 column. So I have something for A, my coefficient matrix, and something for B, my constant matrix, in my calculator. And then I'm going to call on, get out of that. I'm going to call on matrix A, but I got to use its inverse, and then multiply it by matrix B. My solution should be 2, -1, -2. Most important thing here is don't do A times B. Okay. You have to know that the solution to your matrix equation is A inverse times the constant matrix. Okay, so the inverse times the constant. And I would just say in my final answer, I'd write that as an order triple. That would be 2, -1, -2. Okay, so I want you to practice tonight on the homework. I want you to practice doing it with the inverse matrix. Don't keep doing reduced row echelon form and REF, because you want to make sure that you feel comfortable with the other ways. You can, though, take stock after doing your homeworks. Why would I ever do a matrix equation if I love RREF in my calculator? Then I get it. You would do RREF in your calculator, but you're at the learning curve, so you want to know both ways. Does anybody have any questions? Okay, do you have any questions on your homework assignment from Friday? The multiplication